you so much for the introduction and the invitation. So everything I'm going to say today is joint work in progress with Josh Lam, and I'll also briefly mention some joint work with Monica. All right, so for me, the thing that makes algebraic geometry special is that objects of algebraic geometry are infinitary. They're defined by finite coefficients and polynomials with finite many coefficients. I have to move down my microphone. Is that better? Okay. And so they all decided to find a generated the algebras, and they have arithmetic. And I think we've understood, probably before anyone in this room was born, that there's some interactions between the arithmetic of a variety or other algebraic geometric object and its complex geometry. So typically this is mediated by cohomological invariants. So for example, when you prove the Bay conjectures, you show there's this realization of the cohomology of an algebraic variety, Litt cohomology, which is related to counting points. And then that has some compatibility with singular cohomology. So point counts control something about the cohomology in characteristic 0. So for this talk, the motivating example will be Katz's proof of the p-curvature conjecture, the cohomology of algebraic varieties. So for linear differential equations come from algebraic geometry. But what I'd like to do is talk about some things that go beyond the linear situation. So some results about nonlinear differential equations in algebraic geometry. And how their arithmetic reflects their complex geometry. Okay, so let me start by recalling the linear story. So what's the main conjecture about algebraic differential equations? In my view, it's the Grothendieck-Katz p-curvature conjecture. And here's a simple situation. So take a linear differential equation. So f is a vector of functions, and you want to solve the equation f prime equals a times f. And the question the Grothendieck-Katz p-curvature conjecture tries to answer is when can you explicitly write down the solutions? So when are they algebraic? So in the algebraic closure of the field of rational functions in one variable. And the answer is a simple arithmetic condition. Or the conjectural answer is a simple arithmetic condition. You take this differential operator to the pth power, and you ask that it be 0 mod p for almost all p. Okay, so what's known? Well, the forward direction is very easy and the backward direction is very open. But I just want to stress, I mean, I've written it in a very arithmetic looking way, but the content of the backwards direction is you want to prove a statement of complex geometry. You want to show that the analytic solutions to this differential equation are finitely branching, that the monodromy of the differential equation is finite. So let's do an example. So here's maybe the simplest differential equation you can write down, f prime equals af over z. So what are the solutions? Yeah, so z to the a, or constant times z to the a. And this is algebraic if and only if a is a rational number. And let's just check that that's the same as this differential operator to the p to the power being 0 mod p for almost all p. Well, here I just computed what it is when you take it to the p to the power and apply it to a binomial. And you get some kind of falling product, so n minus a times n minus a minus 1 all the way up to this. So you want that to be 0 mod p, and it's easy to see that this is the same as a being an integer mod p, and that happens mod.
Sorry, the Zoom is coming off part of the screen. Do you have any idea?
I don't know what to do about that.
I'm not. Okay, I'm not sure what to do either.
Maybe let's move it along for now. Yeah, and it's a consequence of the Cherepanov density theorem that this happens for almost all p if and only if a is a rational number. So this case of the p-curvature conjecture is already related to some deep number theory of the Cherepanov density. It'll be convenient for us to have kind of a stronger form, or well, an equivalent form, but maybe more flexible form of the conjecture, which is for linear differential equations in a more general setting, so those parametrized by a more general smooth variety. And here's the conjecture. So you have a flat vector bundle, and the conjecture is that, well, all the solutions to the corresponding differential equation are algebraic. It's the basis of flat sections. If and only if some invariant, its p-curvature, is 0 mod p for almost all p. So let me recall what this means. So first of all, what's a flat vector bundle? You should think it's just a vector bundle with a rule for differentiating its sections. That rule has the property that makes partials commute. That's what it means to be flat. Does it mean to have a basis of algebraic flat sections? It means this flat bundle is trivialized on a finite étale cover of X. And then what is this p-curvature operation? Well, it's something funny. It measures the difference between applying nabla to v and then taking the pth power, or applying nabla to v to the pth power. So here, in characteristic p, take a vector field, it's pth power, and get a new vector field. Okay, but concretely, what does this mean? If you take a vector field like ddz, so coming from some tall coordinate system maybe, so something where it's pth power 0, the second term vanishes, and then it just becomes this, which should look familiar. So if your differential equation, ddz minus a f is 0, then it's saying that ddz minus a to the p is 0 mod p. We're almost solved. Okay. So I think the main evidence, we have I would say, kind of meager evidence for this conjecture. The main evidence is the result of Katz, which I'll make precise soon, which is that the conjecture is true for linear differential equations coming from algebraic geometry, so Gauss-Manin connections, we saw in Javier's talk. There's some more evidence too. So for example, we know it for differential equations with solvable or virtually solvable monodromy group. Okay. So here's what Katz proved in 1972, more than 50 years ago. So x to s is a smooth proper family over, let's say, the ring of integers of a number field. And we've associated a flat bundle to it, which Javier explained to us. It's the bundle which is given by the ith cohomology of the fibers equipped with the Gauss-Manin connection. You can describe that complex analytically here. It's the bundle whose monodromy is given by the action of pi1 of the base on the ith cohomology of a fiber. And the miracle proven by Katz and Oda is that this actually is an algebraic flat bundle with an algebraic connection. Okay, so here I guess maybe classically you can think of these differential equations as the ones satisfied by period functions, like in Javier's talk, and their monodromy controls something about the topology of this map. And what Katz did is he proved the p-curvature conjecture for these bundles, and later in the talk I'll recall something about his proof. But maybe let me just remark the content is to show something geometric, namely that pi1 of the base acting on the cohomology of a fiber, that action in fact is through a finite group if the hypotheses of the p-curvature conjecture are satisfied. So the p-curvature of this differential equation controls something about the topology of this map. All right, so the question I want to talk about for the rest of the talk is, what about nonlinear differential equations? So I have to first tell you what people expect to be true about algebraic solutions to nonlinear differential equations. So what's the p-curvature conjecture for those? And then what are nonlinear differential equations coming from algebraic geometry? So what are the analogues of the Gauss-Manin connection? And Ellen briefly alluded to these in her talk. Okay, so what we'll do is, instead of taking singular cohomology of a variety, we'll take the space of representations of pi1 into SLR up to conjugation. And here I'm taking a GIT quotient. So points of this affine variety, complex points of this affine variety really correspond to semi-simple representations of pi1 into SLR. And I think there's a general philosophy, which I guess I learned by studying work of Simpson and of Alen, that maybe one should think of this as some analog of cohomology. And in fact, many of the statements you expect to be true about cohomology of algebraic varieties should have analogs for this space and its various avatars. Okay, and the goal of this talk is to prove at least an analog of Katz's result, where you replace cohomology with this kind of nonlinear object. Okay, so I'm going to start the nonlinear story now. Maybe before I do that, are there any questions about the linear story? Okay, so first I should tell you what is the nonlinear version of the p-curvature conjecture, and I'll give a couple different explanations of that. So here's what you expect to be true for a sort of classical nonlinear differential equation. So here I've written the nth derivative of f is equal to some rational function in z and the first n-1 derivative. So this is maybe not quite the most general kind of nonlinear differential equation one can ask about, but we'll discuss something more general soon. And so here's a conjecture. So this is a sort of concrete form of a conjecture, which I think the first appeared in unpublished work of Eck et al., Shepard-Baron, and Taylor, and then maybe first appeared in print in beautiful work of Bosch, where he resolved some special cases of it. So what you do is you write down this funny vector field. So here the relationship between this differential equation and this vector field is just that you put this same g in the last coordinate. And the conjecture, so the p-curvature conjecture for this kind of nonlinear differential equation is the following. So it's that all solutions to this differential equation are algebraic, so algebraic functions. If and only if, when you take this vector field v to the pth power and you reduce it mod p, that's 0 for almost all times. Okay, so maybe before moving on to a more general version of this conjecture, let me kind of say where this vector field V comes from. So it's actually something you've all seen in like your first calculus course. So what this is a phase portrait for the differential equation. So it's some vector field whose flow lines are naturally in bijection with solutions for this differential equation. You can write them down. It's like you take the solution, its first derivative, its second derivative, and so on. And here I've graphed a phase portrait for some logistic nonlinear differential equation. Okay, so this is some quite general conjecture for which we have even less evidence, I think, than the linear version of the p-curvature conjecture. Let me tell you a slightly stronger version that we'll need. So here, what is, I think, maybe the most general version of a differential equation where you have analytic local solutions? It's an integrable foliation. So here, F is a subsheaf of the tangent sheaf of the smooth variety, which satisfies some conditions I'll write down shortly. And the conjecture is that the leaves of this foliation are algebraic if and only if F satisfies some arithmetic property. So it's closed under p powers when we reduce it mod p for almost all p. Okay, so let me just make explicit what that means. So F is a subsheaf of the tangent sheaf. You can take a section to that. That's a certain class of vector fields. And you can raise them to the p power. That gives you a new vector field, and you want that vector field to still be an F. Okay. So maybe let me just remind you all what a foliation is and slightly expand, define these red words here. So this is a foliation. So I've been teaching in Canada for a while now, and I've learned that I should relate my lectures to my students' lived maple syrup experience. So that's where this picture comes from. Okay, so what's really a foliation? So it's a subsheaf of the tangent sheaf, which is closed under the Lie bracket, right? So the tangent sheaf is a sheaf of Lie algebras, and I would like F to be also closed under that, closed under the Lie bracket. This picture here, is supposed to capture that. This gives you a way of writing your space locally analytically locally as a product. So in other words, at each point of your space, you have a subspace of the tangent space, and you'd like those to all glue together. You'd like them to integrate analytically to leaves. And then here, this condition is what you need to do that. It's some nonlinear analog with mixed partials to meet. Okay, so what is a solution? Well, it's what you get when you glue your local tangent spaces together. And here I've written down the definition of a leaf. So it's just a analytic subspace of X. So that the induced map on tangent spaces gives you an isomorphism between the tangent space of your subvariety and your foliation. But really, you should just think it's a solution to your differential equation. Okay, so this is the conjecture. The goal of the talk is to prove the conjecture for nonlinear differential equations coming from algebraic geometry under what I hope you agree are kind of mild hypotheses. Okay, so next I have to tell you what are nonlinear differential equations coming from algebraic geometry. So I think when I say linear differential equations coming from algebraic geometry, I mean Gauss-Manin connections. So I have to tell you what is the non-abelian version, the nonlinear version of a Gauss-Manin. Okay, so, well, the Gauss-Manin connection came from taking cohomology of algebraic varieties. To get something nonlinear, we want to take some kind of non-abelian cohomology of algebraic varieties. And just like cohomology, non-abelian cohomology has a lot of different incarnations. So with cohomology, you can take singular cohomology, run cohomology, and Gauss-Manin connection kind of captured something about the relationship between those two objects. So here we'll have a version of non-abelian cohomology, which is analogous to singular cohomology, and a version which is analogous to de Rham cohomology. So here, X is going to be a smooth projective variety. I already briefly told you what the Betty moduli space of X is, but let me recall it. So it's this, you take maps from the pi1, the usual topological pi1 of X into the special linear group, and then you take that's some affine variety, and then you take the spec of the invariant functions on that under conjugation by SLR. So the complex points of this are the same as semi-simple representations of pi1x into SLR up to conjugacy. There's another way of thinking about this, which is, well, each local system on X, each representation up to conjugacy, gives you a flat vector bundle. So you can take the de Rham moduli space of X, which is the space of flat bundles equipped with an isomorphism between the determinant and O, and that's just to make sure the monodromy lens in the special linear. I mean, everything I'm going to do, you could also put another group there, but just for concrete, let's stick with SLR for now. Okay, and analytically, it's a kind of famous fact that the two complex analytic spaces associated to these varieties are biholomorphic to one another. That's called the Riemann-Hilbert correspondence. How does it work? Well, given a local system here, you tensor with O, that gives you a vector bundle and it's equipped with a flat connection. Given a flat connection, you take its kernel, that gives you a local system. And just to be explicit, what is the analogy here? You're supposed to think this Betty moduli space is the analog of singular cohomology. The de Rham moduli space is the analog of de Rham cohomology, maybe algebraic de Rham cohomology. And here, this is the analog of de Rham's theorem comparing de Rham cohomology and singular cohomology. Okay, so before I continue, just a warning. These are spaces, they're typically highly singular, and I'm going to make a lot of statements that only make sense a priori on the smooth locus of these spaces. So you have two choices. You can just trust me that one can make sense of these statements on the singular loci as well, and many people, including Simpson, have figured out how to do so. Or every time I make a statement, you can just replace these varieties with the smooth locus, and you'll still get true statements. Although the proofs of those statements, especially later in the talk, will have to go through some possibly singular loci. So in the proofs, you are not allowed to replace these spaces with their smooth loci. So what is the non-abelian Gauss-Manin connection? So recall that if you had a smooth proper family, the Gauss-Manin connection was a differential equation whose monodromy captured the action of pi1 of the base on the cohomology of the fiber. And there's a non-abelian version of that exact same setup. So if you have a fibration like this, there's an outer action of pi1 of the base on pi1 of the fiber. If you'd like, you can think of it. There's a map from S to B diff of the fiber, for example. That gives you this data. Okay, and that's enough to get an action of pi1 on the base on the Betty moduli space of the fiber. So the outer automorphism group of a group acts on conjugacy classes of representations. So if you have a pi1 equipped with a map to the outer automorphism group, that gives you an action on the Betty moduli space. Okay, and I claim that this is enough to define some kind of foliation on a relative moduli space of flat connections or of representations. So to define that, I'm going to set S tilde to be the universal cover of S. And here I'm going to make a definition. I'm going to twist the Betty moduli space of the fiber by the action of pi1. Okay, so here, for now, ignore the right-hand side of this diagram. So all I've done is taken the sort of fiber bundle over S, whose fiber is given by the Betty moduli space of a fiber, so representations of pi1 of a fiber, except I twisted out by this pi1 action on the Betty moduli space. So this is some map whose fibers are all isomorphic to the Betty moduli space of the fiber of pi, but that isomorphism is not, you can't make it equal. You've twisted it by the pi1 action. Okay, anytime you make a product construction like this, you get a foliation for free. Well, why is that? I told you a foliation is a description of your space locally as a product, and well, here I took a product and I quotiented it by some group acting, freely discontinuously, and so that doesn't destroy the local product behavior. Okay, so this Betty moduli space is a family, it parameterizes kind of families of representations, and this foliation, leaves of it correspond to families of representations which are locally constant up in conjugacy, and that makes sense because all the fibers of this map are homotopy equivalent. So if I have a representation of pi1 of two nearby fibers, well, that's representations of the same group. You can ask, are they conjugate to each other? Okay, on the other hand, this Riemann-Hilbert correspondence works in families. So you can take the relative moduli space of flat bundles on X over S, I guess I should say with trivialized determinant. Again, something not totally obvious happens. So I think this was written down first explicitly by Simpson. This foliation, which I described in a purely analytic way over here, becomes algebraic. Okay, and again, you can understand what its leaves mean complex analytically. The leaves are families of flat bundles whose monodromy representations are locally constant conjugates. Okay. And this is the foliation where I want to study this non-linear version of the p-curvature for the rest of this talk. And maybe just to make things a little bit more concrete. So it's not too hard to see that this foliation is horizontal over S. So it kind of maps isomorphically onto the pullback of the tangent bundle of S to the de Rham moduli space. So what you can do is you can think of it as a rule for lifting tangent vectors on S. So each vector field on S is equipped with a canonical lift here. And well, let's just say pretend S was an open subset of the affine line and you took the vector field ddz. So this would give you a canonical vector field upstairs corresponding to ddz. So this looks just like our picture, our phase portrait picture from a couple slides ago. Okay, concretely, what does this mean? It means if you take a point here, so a flat vector bundle on a fiber of pi, and you take a little deformation of the point of S it lives over, you have a canonical recipe for deforming your flat bundles with a nearby fiber. So just to, I mean, I think the way I've described it, it looks like this really fancy object, but it's really, really classical. So I think maybe the.
Can I ask a question about
Yeah.
that slide?
Yeah.
Say foliation becomes algebraic. That only means something about beliefs being algebraic subvariety.
No, definitely not. So I mean, this subsheaf of the tangent sheaf is algebraic. That was on the smooth locus. What I really mean is that this is a crystal over S. That's the precise thing to say. And the question we're trying to ask is when are the leaves algebraic, right? So in general, if you have a different algebraic differential equation, its solutions are not algebraic. And the question the p-curvature conjecture tries to answer is when are the leaves, when are the solutions algebraic? And so in general, these leaves are very far. Right? They're typically infinitely branching and quite wide. Okay, and maybe just to stress that. So okay, I think these are the first examples of non-abelian Gauss-Manin connections or isomonodromy foliations that people wrote down. So the Panlevet 6 equation was not written down first by Panlevet, it was written down first by Fuchs in 1905, more or less from this point of view. So he was studying connections on P1 minus 4 points, and then how to isomonodromically deform them as you move the points around. And then more generally, Schlesinger in 1912 studied the sort of general connections on P1 minus n points, and this is the differential equation that controls how to deform them. And here, I guess this doesn't quite fit into the story I've told because these are isomonodromy problems corresponding to non-proper varieties. But in fact, for any family of curves, we get a isomonodromy differential equation, and you can always put it in this form where you put some constraints on the a's and lambdas. So this is a fairly typical example of an isomonodromy foliation or isomonodromy differential equation that might actually come up. And you can see they're quite classical. Great. So our goal is to try to understand something about the p-curvature conjecture for this class of differential equations, and in particular, how the arithmetic of these differential equations reflects something about the geometry of your map pi, your x over s. Okay, so let me tell you the results. Start by recalling the result which motivates all this, which was Katz's result. So we have x over s, you take the cohomology of the fibers. This gives you some flat vector bundle. And Katz proved the p-curvature conjecture for this flat vector bundle. He says that if the p-curvature vanishes mod p, well, actually only for infinitely many p, in this case, we don't need almost all p, then, then the way I've written it is the action of pi1 on the cohomology on the integral cohomology of the fiber factors through a finite group. So it turns out this is the same because this connection, as Elaine explained to us, has regular singularities as having all of the solutions being algebraic. So this is a reformulation of what Katz proved, and I'll recall the proof in a few slides. Okay, so the first theorem I want to tell you about is, I think, a fairly strong non-abelian analog of this theorem. So this is joint work with Josh. It's not yet available, but hopefully quite soon. And it's the exact same statement where you replace cohomology with the moduli space of flat connections. Okay, so you have x over s smooth proper. You take this moduli space of flat connections on x over s, equipped with this non-abelian Gauss-Manin connection, the isomonodromy foliation. And then you assume that this foliation is closed under p powers mod p for almost all p. So here, I wrote the p-curvature of the foliation vanishes mod p. That just means that the foliation is closed under taking p powers. And then the theorem is that the action of pi1 of the base on the z points of the Betty moduli space of the fiber, so representations of pi1 into, well, at least with traces valued in z, factors through a finite. Okay. So you could ask, does this resolve this p-curvature conjecture for the isomonodromy foliation? And the answer is no. Okay, so why is that? Well, for example, this is some random algebraic variety. It could have very few z points. So knowing what happens when you act on the z points, it doesn't necessarily tell you much about the geometry of this foliation. So in order to prove this p-curvature conjecture, you have to replace this z with a c. If you could actually show that the pi1 of the base action on the complex points of this Betty moduli space factored through a finite group, we would have proven this p-curvature conjecture for isomonodromy foliation. So it's not totally obvious. It's true.
A small question is, you wrote infinitely many p, but earlier you need almost all p.
Yeah, so this is just like in Katz's theorem, you only need infinitely many p, and in this case, because there's sort of, yeah, so maybe let me make a remark about sort of a sort of important open question in the p-curvature conjecture. So you could ask, is the p-curvature conjecture true for some ends of Gauss-Manin connections? For some ends of Gauss-Manin connections, and that we don't know. So the Katz's result doesn't apply there. Yeah, so we know it if there's a five-group connected motivic Taylor group by Andre. We don't know it in general. And it's not hard to see that if you just want to prove it for some ends of Gauss-Manin connections, then you need density one. A density one set of primes. So here also, just like in Katz, when you take the whole around moduli space, you only need the foliation to be closed under p powers mod p for infinitely many p. But I think if you try, you can formulate versions of this for subvarieties of the moduli space, and then you would almost certainly need density one. Well, I'll tell you an improvement very soon. You know, even without it. Yeah. So maybe let me just say. So here was Katz's theorem, right? So why does this imply the p-curvature conjecture for Gauss-Manin connections? Well, you want to show that the action of pi1 on the singular cohomology with complex coefficients factors through a finite group. That's just you take this finitely generated abelian group and you tensor it with C, right? So if you have a z to the n and an action on it which factors through a finite group, then that action also factors through a finite group when you look at the induced action on C to the n. But here, this is a kind of nonlinear object, so just knowing what happens on the z points is not enough to tell you what happens on the C points. So we're really kind of what makes this challenging is this is not a vector space. So not quite. So in fact, I've stated something less general. So if you replace z with any ring of integers here, we win. The problem is that we don't get a uniform finite group. So in principle, yeah. Yeah. So if you could do it uniformly in the then you would. Oh, I'm sorry. Not. You would have to do it with S integers, I think, because you don't know. I mean, this could have like no z bar points. Right. This could have no z bar points, like except for the identity or something. Right. So even if you know it just for rings of integers, you. No. So this we don't know this. I mean, I guess you've proven sometimes. We'll talk about this. This variety has some z bar points, but we don't. If you just have a statement about the action on z bar points, you might not win. Yeah. Okay. So here's what we prove. So here's the cases under which we can resolve the p-curvature conjecture for these foliations. So the same hypothesis as before. So suppose the p-curvature of the foliation vanishes mod p for infinitely many p, meaning the foliation is closed under p powers when you reduce mod p. And suppose further that each component of this space contains a smooth z-bar. So then the statement is that the p-curvature conjecture is true in this case. Okay, so let's. So in other words, the action of pi1 on the base on the set of semi-simple complex r-dimensional representations into SLRC factors through a finite. Okay, so this tells us that the arithmetic of this foliation controls something about the geometry of this map. Okay, so let's try to understand how strong a hypothesis is this red condition. So when do we know that this moduli space contains a smooth z-bar form? Okay, so I would conjecture it's basically always true. So I would even conjecture that z-bar points are Zariski dense in the complex points of the Betty moduli space, and that at least if the Betty moduli space is reduced, that would imply there's always a smooth z-bar point. Okay, so when do we know that? So as far as I'm aware, there are two cases where we know this is true. So the simplest case is when R is cubed. So we're looking at two-dimensional representations, and this is joint work with Simone and Koche, who will, I think, talk about it tomorrow in one of the contributed talks. And then the other case, which is quite a bit deeper and relies on the Langland's program theory of companions, is due to de Jong and Hainaut, in the case where the Betty moduli space is irreducible. So in this case, combining their work with the older work of Rumley, one finds that z-bar points are actually even analytically dense complex points. Yeah.
So we made the assumption to doesn't really come to.
Yeah, I think I got it okay. Maybe we can discuss that. Yeah, Phil, did you have a question?
I was wondering if you like take out of pi one, and then that maps to like say the permutations of the integral points. Do you have an example where that has an infinite kernel? Or
Repeat the question.
Yeah, so can the action of pi1 on the Betty moduli space have infinite kernel? Is that the question? Or on this just to the z points of the Betty moduli?
yeah, if you map to say the permutations of the z points.
I would, oh, it's the z points as opposed to the z bar points.
Yeah.
I don't know an example. I know an example if you allow me to take relative character varieties. I would have to think a little bit if you want the smooth proper setting. But I think the answer is morally it couldn't be huge. I mean, well, in the case I'm in where y is smooth and proper, there's always a z point because there's the trivial representation. Yeah, but probably there are lots of examples with basically no z points. So I would think. Yeah. So if you take p1 minus 4 points with sort of some choices of local monodromy, there couldn't be no z points at all. So yeah. Yeah. Okay, and then so just combining this theorem and theorem 2, you get an immediate corollary, which is you can prove the p-curvature conjecture for this isomonodromy foliation, the non-abelian Gauss-Manin connection, well, under the conditions that we know the conjecture. So if R is 2, we have an incomplete generality. And if the Betty moduli space is integral, then we know it. I expect this integral can probably be weakened to irreducible with only a little bit of work. Okay. Are there any questions about these statements? Okay. So this is the main result at the top, and I want to explain. For me, I think it's a fun result, but for me, it's really an excuse to think about kind of what structures exist on the non-abelian cohomology of an algebraic variety, and like to what extent can Katz's argument in the abelian setting be imitated. So for the rest of the talk, I want to kind of recall what Katz did and then say how we copy it. Okay, so what does Katz's proof use? So, well, he's studying the cohomology of an algebraic variety, and cohomology has a huge amount of structure. So here you can see a list of things, some of which we already understand, like the Gauss-Manin connection. Maybe we understand what the non-abelian version is, but there's all this structure. So in particular, like the Hodge index theorem, that when I started thinking about this problem, I didn't really know how to think about it in a non-abelian way. But we really need non-abelian versions of all the structure to prove the theorems that I've enunciated here. Okay, so let me recall what Katz did. So I guess Plato said that all knowledge is recalling things. So maybe I'm only recalling it in that sense, but I don't assume that you've actually thought about this before. So what did Katz prove? So you have a smooth proper map. Associated to it is some differential equation, and you assume the p-curvature of that differential equation vanishes mod p for infinitely many p. You want to show it's finite monodromy. Okay, so there's 3 steps. So the first step is algebraic. He shows that if the p-curvature vanishes for infinitely many p, then the Gauss-Manin connection preserves the Hodge filtration. Okay, I'll say a little bit more about this shortly. Then there's an analytic step, which is that if you have a z variation of Hodge structure, where the connection preserves the Hodge filtration, well, then it also preserves the polarization. Sorry, I should have said a polarizable z variation of Hodge structure. But we understand how the polarization on the cohomology of a family of algebraic varieties interacts with the Hodge filtration. And so what you can do is you can modify it to get a unitary inner product. So pi1 actually acts on the cohomology of the fiber in a unitary way. And then finally, well, now you know the action of pi1 on the cohomology of the fiber factors through GLRZ, intercept the unitary group. Oh, well, Z because this singular cohomology has a Z structure on it. And the intersection of these two groups is a finite. So you okay. So I think probably most of you have this being a Hodge theory session, probably most of you have seen the definition of a polarization, so I won't expand too much on like the input from the Hodge index theorem here. But let me just say a brief word about this algebraic step. So somehow you have to connect the p-curvature to the obstruction to the Gauss-Manin connection, preserving the Hodge filtration. And what Katz shows is that there's some filtration on de Rham cohomology mod p, so that the associated gradient of the p-curvature with respect to that filtration is identified after Frobenius twist with the obstruction to the Gauss-Manin connection, preserving the Hodge filtration. So that's captured in the commutativity of this kind of complicated diagram. I'm not going to say what the conjugate filtration is, which is what Katz uses, but so really all you need is that filtration with these properties exists. Okay, so this is what Katz did. So somehow he finds a connection between the associated gradient of the Gauss-Manin connection, the Kadir-Spencer map, and p-curvature. Then he uses the Hodge index theorem to get some unitarity, and then he uses the Z structure and the unitarity to get finiteness. Okay, so I've kind of highlighted all of the things that maybe seem problematic in the non-abelian setting. So you have to figure out what is a filtration, what is the associated gradient, what is the associated gradient of the p-curvature, what is the associated gradient of the Gauss-Manin connection, what does it mean to be unitary, what is the Hodge index theorem. Okay, and so in the last 14 minutes, I want to explain that. Are there any questions before I do so? Okay, so let's first of all talk about what a filtration is. So in Katz's argument, you need two filtrations, the Hodge filtration and this thing called the conjugate filtration. And here Simpson tells us what to do. So let me tell you what a filtration on the de Rham moduli space is. So it's a space Q with a GM action, a GM equivariant map to A1, where GM acts on A1 via scaling, and identification between the fiber over 1 and the de Rham moduli space. Okay. And then we're just going to make a definition. I'll call the associated gradient of the de Rham moduli space with respect to such a filtration the fiber over 0. Okay. And the motivation, I think, for this is that it's also a fun exercise if you get bored, is that there's some equivalence of categories between GM equivariant vector bundles on A1 and filtered vector spaces, or finite dimensional filtered vector spaces with an exhaustive filtration. Okay, so what I want to do is I want to just, well, recall for you definitions of two filtrations on the de Rham moduli space analogous to the Hodge filtration of okay, so first of all, what's the non-abelian version of the Hodge filtration? So I think this is due to Simpson. So what it is the moduli space of lambda connections. So here you should think lambda is a number. And what is a lambda connection? It's a vector bundle with a map that looks kind of like a connection, except the Leibniz rule is twisted by this number lambda. So if lambda is 1, you get a connection. If lambda is 0, this is something O-linear. And then there's also a flatness condition. So this is the non-abelian version of the Hodge filtration. And what's its associated gradient? Well, it's something that's probably familiar to many of you. So what's the fiber over 0? Well, when lambda is 0, this just says this map is O-linear. So here, gamma of f times f is s is f times gamma of s is what it means to be O-linear. And here, so here we have things with an O-linear map whose square is 0, and that's a Higgs bundle. So what this says is that the associated gradient of the moduli space of flat connections with respect to the Hodge filtration is the moduli space of Higgs bundles. There's some stability conditions that I've omitted from the slide. Probably written. Okay, so what's the non-abelian version of the conjugate filtration? So as far as I know, this is maybe first written down by Menzies, although it needs to be modified slightly. And maybe I should say, I think this question of studying the p-curvature conjecture for isomonodromy foliations was probably first thought about by Kissen, and then I think a number of his students have thought about it. So I don't know, Anams has done related work, but also Papaneau and Menzies. So okay, so here's what I think the non-abelian version of the conjugate filtration should be. So you take triples E nabla phi, where E nabla is a flat bundle, and phi is something which equals the p-curvature up to your scalar lambda. Okay, and has to satisfy some conditions. Okay, and now it's a little exercise to work out what the associated gradient is. So this is an application of Cartier theory. So what's the fiber of this thing over 0? Well, all it says, if lambda is 0, this says that the p-curvature is 0, and then phi is any horizontal map which squares to 0. And if you work this out, you see that this is the moduli space of Higgs bundles on the Frobenius twist events. Okay. So another way of saying that is that the associated gradient of the Hodge filtration is up to Frobenius twist, the associated gradient of the conjugate filtration. In the abelian setting, that's what's called an F-zip structure. in this commutative diagram of Katz, it's the two horizontal arrows in the square. Okay. So now I have to tell you what the vertical arrows are, and I won't actually do that. I'll just tell you that that they exist. So there is a non-abelian version of Katz's formula. If you ask me about it after the talk, I can tell you what the analog of the associated gradient of the p-curvature and the associated gradient of the Gauss-Manin connection are. But we show that they're the same up to Frobenius twist under this identification from this previous slide. And in particular, a consequence of this is that if the p-curvature of the isomonodromy foliation vanishes mod p for infinitely many p, the non-abelian Gauss-Manin connection preserves the Hodge filtration. Okay, what does that mean in the non-abelian setting? I think it's kind of clear what it means if you have filtered vector bundle for a connection to preserve the filtration. But here, remember, a filtration was a family over A1, so a degeneration of the de Rham moduli space to the moduli space of Higgs bundles. And what it means is, well, on the fiber over 1, and hence on every fiber away from 0, this thing carries a foliation. And what it means is that the foliation extends across the central fiber. So what this theorem says is that if the p-curvature of the isomonodromy foliation vanishes mod p for infinitely many p, then the foliation extends to the moduli space of Higgs bundles. Okay, and just some remarks. So the proof of this last step relies on August Wallengotsky's work on non-abelian Hodge theory and positive characteristic, and it has a precursor. So Menzies proved this last statement under the assumption that X over S has a Frobenius limit. All right, so this is the non-abelian version of Katz's formula. Okay, so let's just take it as given now and try to prove the rest of the theorems. So the other thing we needed was the Hodge index theorem. Right. So what is the non-abelian Hodge index theorem? So let me just say what the, so I don't think what I'm going to say is the last word on a non-abelian Hodge index theorem. I think there's more one would want, but what we do is we prove the consequence of the Hodge index theorem that Katz uses. So let me remind you what Katz used. So if you have a variation of Hodge structure, a polarizable variation of Hodge structure, where the connection preserves the Hodge filtration, then the associated monodromy representation is unitary. So that's what Katz used. And in fact, we found kind of two analogues of this statement, which turned out to be useful to us. So one consequence of a representation being unitary is that if you take any vector and you look at its orbit under your group action, it has compact closure. Okay. And the first part of this theorem says that if the non-abelian Gauss-Manin connection preserves the Hodge filtration, so meaning it extends over the central fiber of the moduli lambda connections, it gives you a foliation on the moduli of Higgs bundles. And so in particular, if the p-curvature vanishes mod p for infinitely many p by the class theorem, then the orbits of pi1 of the base on the complex points of the Betty moduli space all have compact closure. So you should think this is some kind of non-abelian version of being a unitary representation. Okay. So that's the first analog of the Hodge index theorem. The second one is that under the same hypotheses, this action preserves the Kähler metric on the Betty modulus, on the smooth locus of the Betty modulus. And so the proof of this theorem, I'm not going to say much about, but I'll say it's a theorem of analysis. So I mean compact in the analytic topology. Yeah. So this is a proof of analysis. So it relies on Corlett, Donaldson, Simpson's work on non-abelian Hodge theory. I haven't told you enough to explain the proof. It's involved. But if you ask me after the talk, I can say a bit more about it. Okay, but let me just explain. So the corollary is there's a sort of simple corollary, which is suppose we're in the situation where the isomonodromy foliation has vanishing p-curvature, then the orbit of any z bar point under pi1 of the base is finite. And let me just give you the proof when you have a z point instead of a z bar point. The case of z bar is only notationally more complicated. Well, if you have a z point, the set of z points in this affine variety M Betty is discrete. And we just said that this orbit has compact closure. So if you're discrete and compact, then you are finite. So this theorem, well, it doesn't quite imply immediately the statement I made before that the action on the z points factors through a finite group, because I haven't explained why it's uniform in the point. But this is the content of that theorem. Yeah, clear question? Yeah.
What is the occasion If you handle the Galois conjugate.
Yeah, you have to handle all the Galois. But the point is, all the Galois pundits are also have contact closures. So you do some data description. So
Well, I'm confused because your fundamental group action is somehow analytic, right? So you're going to use in this case for the.
So it sends Z bar point. It sends an OK point to an OK point. If you think about what it is, right? It's just you conjugate a representation. By an so you map from pi1 to GLN OK. You act by some outer automorphism of pi1. It still maps to GLN OK. Yeah. Yeah.
So, could you go back to the previous slide? Yes. I was just wondering, so here is pure, but you say it doesn't seem to follow in any useful way from all the products, unless you assume some kind of predictability.
Yeah. So this first clause does not use Opus-Vologodsky, and the second clause does.
So you need some predictability.
That's right. And we are in some mixed characteristic situation because the assumption is about. Yeah, sorry, maybe I should have written more about the setup, but here we have infinitely many p in it, so you're given a lift. But yeah, I don't know. It's sort of very natural to ask. So the issue is that we don't really understand the geometry of this conjugate moduli that stat. Opus-Vologodsky gives you some kind of understanding in a small neighborhood of the nilpotent cone, which is enough for us. Okay. Great. So these are the two ingredients. Let me just kind of say a word about how to put them together to get this theorem 2, which is that if you have a smooth z-bar point in each irreducible component, then you've proven this p-curvature conjecture for the Gauss-Manin connection, or non-abelian Gauss-Manin connection. So let me remind you what the theorem was. So you have x over s is a smooth proper map. You assume the isomonodromy foliation satisfies this arithmetic condition, and you assume that each component has a smooth z-bar point. And then the statement is that all the leaves of the foliation are algebraic, and I claim it's enough to show that the action of pi1 of the base on the Betti moduli space of the fiber, the space of representations of pi1 of the fiber, batches through a finite group. And so here's a sketch of the proof under, again, just a notationally simplifying assumption that instead of a smooth z-bar point, you have a smooth z point on every component. So what do? You pick a smooth z point. Well, it has finite orbit, because its orbit is compact and discrete. So you pass to some finite index subgroup of pi1 that fixes this point. Now, this finite index subgroup of pi1 acts on the tangent space of your point. And that action is unitary because we said the action preserves the K-limit. And it's a unitary action on the tangent space at a z point, smooth z point, and that has a z structure. So you win again because you're taking the intersection of GLRZ with the unitary group. So you get this gamma action again on the tangent space batches through a finite group. And in general, in Riemannian geometry, if you have an action on a Riemannian manifold which acts trivially on the tangent space at a point, it's actually trivial. Some little trick with the exponential map. So you get the gamma action on this on the component containing the point you chose to begin with batches through a finite group, and that component is arbitrary. Okay, so let me finish the talk just by recalling the philosophy and saying where we are and what's left. So the philosophy that motivated this argument is that maybe every statement about cohomology should have some analog for non-abelian cohomology. And in this talk, under what I hope you view model hypotheses, like this, for example, if m Betti is irreducible or integral, we proved the p-curvature conjecture. And we found some analog with the Hodge filtration and conjugate filtration in Katz's formula. And then we also came up with some form of the Hodge index theorem. So 2 and 3 were the main inputs to 1. So what's left? I mean, I think a huge amount is left. So cohomology has a lot of structure that this doesn't capture. And the most basic one, which is what we ran into when we needed these z-bar points, is that we don't really have an analog for the z structure. And so, of course, the Betti moduli space is defined over z, but it's really useful to have this lattice and singular cohomology. And we don't yet have an analog of that in the Betti setting. And so I want to just propose this conjecture as one possible analog for it. Z-bar points should be Zariski dense in the complex points. And yeah, maybe let me stop there.
This is previous slide, where did you use this place?
So where did we use what?
There's no just, it takes the last one and say one before.
This one?
Maybe one, Just, no, it's very fast, it's smoothness of.
How do we use smoothness? Yeah. So I mean, it's that we use Riemannian geometry. So we have a Kähler metric on the smooth locus, which we know that the action preserves. So I think it's possible you could run this with a singular point using Goldman Nelson theory, but I haven't written down the details yet, which is why I'm only stating things in this generality. Yeah. So the reason why is this step 3. So I don't know how to, I don't know how to make sense of the Kähler metric, for example, on the singular at the singular points.
So, because the smoothness assumption is a convergical assumption.
Yeah.
So,
Yeah, maybe we can talk more after. Yeah, I think it's quite possible the smoothness can be relaxed, but I just haven't thought it through carefully.
Other question?
In the linear setting, there's lots of like, I guess, algorithms to p-curvature on a computer. In this non-linear setting, I guess, how difficult is it to compute this p-curvature?
I don't know a fast algorithm. I mean, it's you're taking a vector field, you take it to the p power, that involves a lot of multiplication. So, yeah, I have written a computer program that does it. I can do p is 17. I would probably not feel very comfortable doing, you know, p is 900 something. But yeah, it's actually really fun to do. Like so for example, these isomonodromy foliations have some nilpotence properties, just like the Gauss-Manin. So it's kind of fun to see where a p power, the squared power, and so on vanishes. But yeah, I don't have anything I think confidentful to say algorithmically, except just do the most naive thing you possibly can. Really, all I know how to do.
Is it correct you were talking about work that has not yet appeared?
Yeah, this has not yet appeared.
Can you compare it? Can you explain the difference between the previous paper?
Yeah, okay. So maybe let me just say a word about what that is. So Josh and I came up with some other nonlinear version of the p-curvature conjecture, which just asks when is a specific solution to a differential equation algebraic. And so we studied that for isomonodromy foliations, and we proved it for motivic points. So for points which are coming from Gauss-Manin connections. So the way I think about it is, it's when you want to, if you want to prove the classical p-curvature conjecture, that you want to study this kind of question for subvarieties, I claim, of the ground moduli space. And the two cases we now know how to handle are the cases where that subvariety is a motivic point, and the case where that subvariety is the whole thing. That leaves there's a big gap between those two, but you know, the first paper is the case of a point, and this case is the whole variety. I don't know if that answered your question, but that's how I think about the relationship.
This is been for abelian varieties in the abelian case, then it's like exit and conjugate filtration stuff sort of has a concrete description in terms of the p-divisible group. Is there a way of sort of similarly having a description for abelian varieties, this non-abelian stuff?
I think abelian varieties have abelian pi 1, so I think somehow everything you see here can be described in terms of their first homology. I haven't thought through it in detail, so I would say I don't have a great answer to your question, but I would be surprised if you can't translate whatever homologically this world.
The question? I have a question. Can you say a bit more about the compact closure?
Yeah, sure. Let me go to the theorem. Yeah, so the real theorem is there's some, so both of these statements are consequences of one statement which I didn't want to write down. And actually, I owe Bruno and Johan a lot for kind of giving me a hint as to how to proceed here. So there's some real valued function on the Betty moduli space, which is, well, any of these moduli spaces, which is the energy of a harmonic bundle representative of your local system. And what we really show is that under this hypothesis that the non-abelian Gauss-Manin connection preserves the Hodge filtration, so it extends over the Dolbeault moduli space, that energy function is constant under isomonodromic deformation. And that implies both statements. Well, it implies one because the energy functional is proper, and it implies two because it's a Kähler potential. That's the comment. I don't know if that answered your question. That's the argument.
That's my next one.
Great.